Any questions about anything before we get started? So today, yeah.
So on the web scraping assignment, the part 2 for regression, I just want to make sure I understand this correctly. You just want us to do, I guess, a regular linear regression for age versus, or sorry, rank versus like age.
Everything else.
Oh, okay. So
you want to, it's your job to try to find a good model.
Oh.
So you have all these things you want to predict, basically where you're appearing on the page, based on the other stuff that the other information we've collected about those posts.
Okay, thank you.
I just had a question about for some of the linear regression stuff. I was looking through the notes and I know there was different curves that we were trying to fit just in the lecturing box. We're multiplying certain values that we were taking
different
certain
powers.
values we were multiplying together, and others we were taking powers. And I just wondered when you do something like that.
So for that particular example, just like graphically, from looking at it, we could see that it wasn't a linear relationship, it wasn't a straight line. So we kind of knew like, oh, this is the structure. I don't know that I have a good answer in general for when you would like think those would be good choices. Maybe if the plain old linear ones don't work, you just kind of experiment with other things. I mentioned there's a little bonus part. So for this particular example, Hacker News does have a formula. And so that it's not a linear formula, but you can do a least squares regression on the various terms. So I was like, if you do that, it's like, oh, I know that it's like something over h squared or something, then you could, then you would be like, oh yeah, I want to do that.
So you almost plot the points and then try and fit your line to points.
Yeah, I mean, it was easy for the auto example because we were just looking at the one variable, the gas mileage or whatever. Whereas for all these ones, we have so many dimensions, like you can't really visualize it. So I don't know that I have a good answer for like when to try something like that, other than like use intuition and then look at the R-squared and p-values to see if you were on the right track or not. Other questions? So today we're going to talk about the KD tree data structure in a little bit more detail, and we'll go through all the pseudocode for the various operations. And then we'll talk about related data structure that one of last year's students informed me of its existence. It's very similar to a KD tree, but has a really clever, weird twist on it. So we'll get that one too, just because the pictures of them are very, very beautiful pictures. So there's one more way of dividing space into points. That one is kind of cool because it depends even less on the dimension than the KD tree, which we saw could handle a whole bunch of dimensions without too much fuss. The other data structure we'll talk about doesn't even care about the dimensions at all. It's pretty cool. So, all right. So I have these set of points that I'd like to do my range or KNN queries on. Okay. If I wanted to build a KD tree here, what's kind of like the key idea about how that works?
Just give medians to start dividing.
So first I'll find the median, say in the x direction. So maybe this point is going to be my root. And then I split the points in half. And the points on this side, right, I make another KD tree. but I have fewer points. And instead of finding the median based on x, right, I find the median based on y, so maybe that's this point. And then I just repeat this, right? So every level I switch my dimension that I'm looking at the median with respect to, and eventually I'm going to get, you know, little boxes with my leaf nodes where I have no more children to do it. Cool. So we're going to talk about we'll look at the code for actually, you know, how we go about doing this, and then we'll look at the constructor and also the KNN query. The range query is very similar to the quadtree range query. So we'll look at the KNN one, which is similar but has a little twist to it. Okay, so maybe let's start with the constructor. This is a tree structure, right? So the constructor I really want is probably for a node. So let's start with the definition for the node. So my node, we talked about yesterday what was in there. Anybody remember? So we'll have a point. And then we have like that. So I am putting the dimension here in angle brackets, using it as like a template kind of thing, or templates kind of thing. I don't know if you can do this in Java or not. This is kind of a cool C++ trick. And what I have said here is I've basically made sure that the compiler will catch any mistakes if I try to, like, if my levels don't split on the right dimension, if that makes sense. So if I had like a bug where I split on X and then I had a child that also split on X, that would actually be a compiler error because the types don't match. So by putting the dimension as part of my like node structure, and saying that my children are have the next dimension as their split dimension, actually the compiler is going to catch any mistakes I make about getting the dimensions wrong. I could also, I could just have a member variable here for the dimension. That would also work. Another handy thing about this is it actually takes up no space. So the compiler will check this at compile time, and then at runtime, there's actually no memory used for storing my split dimension, which is kind of a nice thing.
Maybe I don't know what dimension is.
Oh, so that's just going to be it's going to refer to x, y, z, and so x will be 0, y will be 1, z will be. So however many dimensions my data has, I will cycle through. This should probably have like a mod total dimensions here, but I'm going to leave that off.
So this is like saying all the splits all.
Yeah. So if I have 2D data, my root would be a node 0. Its children would be node 1s. Their children would be node 0s. Their children would be node 1s. Yeah. Cool. So this is kind of our main data type, right? So when we do this, right? So here our left child, right? All the points here have basically x dimension. Or say, so all of the, if I if at any point in the left subtree of this node, let's say I call it Q for any of those points, they will have a value in this dimension that is smaller than the node here. So I'm splitting, this is like the binary search tree property, right? Everything in my left tree is going to have a smaller value in whatever dimension I'm splitting on. So if this is an X node, they will be to the left of this point. If this is a Y node, they will be below this point. If it's a Z node, they will be whatever spatial direction makes sense on the smaller, they'll have smaller Z values. Then similarly for the right side, right, they'll all have the appropriate value would be greater. The other coordinates could be whatever, right? So this is an X node, right? All of its left descendants will have a smaller X value, but their Y values and Z values could be greater or smaller. I'm not saying anything about that here. Does that make sense? And so we got basically the binary search tree property, but just for the dimension I'm looking at this point. So let's take a look at how we would basically construct a node from a list of points to build our tree. So we basically want to look at the constructor for a list of points. So how do we build this node? So what's going to be stored in this node specifically? So which P is going to be stored in the node that we're making? This is the median with respect to whatever dimension I'm looking at. Right? So somehow we have to find the median, and we have to put the rest of the elements like kind of on the right side of the median. And so the ones that are smaller have to be on the left, the ones that are bigger have to be on the right. What was the algorithm that we talked about that did that? That was the nth element, right? So basically we want to start by finding the median. And this is basically nth element, points, we'll say like points dot size. So we're saying basically put the median element in the right spot, and then partition the rest of the points so that all of the smaller ones are on one side, all the bigger ones on the other. So we could have also called sort here, but sort would be overkill. We don't need to actually sort everything. We just need to find the median and split the rest. And so we don't really care that the left half and the right half are unsorted. Cool. All right. Now what's next? So we found the median. What should we do with that?
Can you explain how we find the median point without sorting?
Yeah. So it's like a little bit of sorting. It's like an incomplete sort is how it works. The algorithm is kind of complicated, but it works. It like breaks up the array into like groups of 5, and then looks at the medians of those groups and does some weird shuffling. It's like an incomplete sort. It's basically the magic of how it works.
Can we use the other statistic we talked last time to find the, just like say 100 points, we just find 50.
So that's exactly what we would do. So if I have 100 points, when I say nth element, I'm basically saying put point 50 in the right spot, and then put everything else on either the left or right side of the grid. So we are using this to do the median, but if I wanted to do split some other way, I could. Right. So I've done my, not really sorting, but my like shuffling of the points so they're where they need to be. Okay. Okay. So now I've found the median point. It's going to be a position, size over 2. So what should I do with that? Store it here. So we'll say now P equals points size over 2. And so I've got my value at this point done. Cool. All right. And now what else do I have to do? I have part of my tree, and I have to build the rest of my tree. So what other member variables do I have to fill in? My left and right children. And so how do I get my left child? So I have already split my data. Okay. So I need to make a KD tree out of that data, but starting at the next dimension. So I'm going to actually make a recursive call to this, an almost recursive call to this constructor, and I'm going to make another node using the left active points. So. So I'm going to make a new node that's of the next dimension. And so if this is an X split, I'm going to make a Y split node. And I'm going to do it with points up to size over 2. And so this is the first half of my shuffled array, right? It has all the points that are, say, to the left of the one I just stored here. Right, I'm going to pass those to the constructor for the next one. Cool. And then I'll do the same thing for the right. So here I'll go from just past halfway, so size over 2 plus 1 will be the first. That'll be the first point to the right of the one I just looked at, right, and then all the way to the end. Yeah.
So I don't know if this is even a thing, but does Python allow for any kind of memory management like this?
It's garbage collected. So the slices will be, so these things here, they would be like aliases. So when I shuffle them, I'm shuffling kind of the original data, which I am carefully choosing as I recurse. I'm choosing like things that don't overlap. So that's actually fine. So this would be okay, Python. We're actually going to implement this stuff in C++, but
Like if you were to you probably wouldn't say, I don't know, do you use Node?
no, I think you would just say node. Yeah.
Is your left line, is that including the size of the
No, so I'm using the Python slice notation where we don't include that one. Yeah.
That means that how are we relative to brackets? How does it know that it's
Yeah. So this value here, basically in C++, I can use it as a constant. So here, when I do like this +1, that's
Sorry, I thought that.
yeah. So whatever this node dimension was, I can add 1 to it. I could do, it should be +1 mod number of dimensions. But. Cool. So right here, I have a Stack Overflow. I did recursion, and what did I forget? Base case. So what's the base case? Yeah. So I can, maybe the easiest thing to do here is, if there are left children. I just look at the size of the subarrays I'm going to pass, and if they're empty, then I just set it to a null pointer. Yeah.
You always want to run out of points there?
Yeah. So you could do something like we did with the quad tree, where you have internal nodes and leaf nodes, where the leaves have a list of points. You could totally do that as well. In this particular implementation, we're just going down until we run out of points. Okay. But yeah, you could totally implement it that way, and that would probably be better cache-wise because you have fewer levels to the tree. The points you get at the leaves are closer together in memory, all that sort of stuff.
So in this implementation, each node is going to have pointers to nodes, or will I have just one single point?
Yeah, so the pointers to its children might be null, but every node stores 1 point and maybe has children. Cool. So does this kind of make sense? So it's again, these tree structures, the code for constructing them is really, really short and nice and elegant and pretty, which is why these are such popular data structures. But I got a better answer yesterday about the KD tree versus quad tree question. Why would you choose one over the other? KD trees are more popular, generally. Quad trees can be represented more efficiently, so you could store a quad tree in like a compressed way. I guess more efficient than a KD tree is one approach. And depending on how you build them, the quad trees can be cheaper. So we're talking about KD trees where we always split at the median point. If you had a different way of deciding where you wanted to split, it could be more expensive. So I don't know if you've met Danny. He's another professor that he taught the database class last summer. You've probably seen him in videos and stuff. No. But he's a graphics researcher, and so these data structures are really important for rendering, where basically you're shooting like a ray through space and you want to know what it hits. Use these types of data structures for that. And when you build them for KD trees, basically you build them to try to like minimize the number of zones that your ray hits. And so it can be expensive to build those to minimize that, where the quad trees are cheaper to build. So those are why you might see either. Yeah, so this is the constructor. Pretty short, pretty elegant, because we're able to use recursion. Yeah.
So I'm still kind of confused about the template-like dimension stuff. So why do we have that dimension 0, 1, 0, 1, 0, 1? So what's the point to have that?
So I need to know for each node which dimension I'm splitting on. Right. So when I search, right, I have to know like which how I'm dividing my space. Right. So it matters when I get to this point. I have to know am I splitting left, right, or am I splitting up, down? Because that's going to have a big impact on my searching. If I get this wrong, right, if I think I'm splitting on up, down, my points are going to be in the wrong spot. So I have to keep track of that. Cool. Other questions on the constructor? What would the tree constructor look like? So just say, root equals new node 0. Something like that, right? So I'm gonna just decide that my root's gonna start splitting based on X, and then just make it up. Cool. Any other questions about that? What's different about this than when you guys talked about binary search trees? There's the different node types. Yeah. Anything else? What are like typical constructor parameters to a binary search tree? Usually none, I think. So typically when we talk about BSTs, right, the constructor just makes an empty tree. And to actually build it, what do? You just call insert like a bunch of times, right? Right, so without, for the unbalanced or the potentially unbalanced case, like the vanilla BST, right, we had to worry about the order that things were inserted, because otherwise the tree might get really imbalanced. Right? If we wanted to make sure the tree stayed balanced no matter what order we inserted stuff in, you saw, I guess in John's class, you saw how to deal with that. What was one of the approaches you might use? Red-black tree, right? So when things get unbalanced, you rotate. Right? So it's kind of harder to rotate here, right? Because we have this rigid structure of alternating levels, right? So we can't actually use like the plain old rotates you talked about, because we'd have the wrong types of nodes in the wrong spot. So for the KD trees, usually we actually know all of the data ahead of time, and we construct them. We do a lot of pre-processing during construction to make sure that they're nice and balanced. And I would say it's less common to actually like insert stuff after construction. So you could totally do that the same way you do insert into a BST, right? You search for it, you get to the bottom, you add a new node. But typically for these applications, you kind of know all of your input points up front. You make the tree once, and then you just search a bunch.
So that pre-processing can be sorted.
Yeah, so this is what you don't do in a normal BST, right? When you insert, you just kind of go one at a time, and the order just happens. Right? Whereas here, we're like very carefully controlling. We're doing the sorting ourselves to make sure that the height is what we expect.
My mental image of this is like very inherently unbalanced. What does the balanced version of this look like?
So this is balanced because when we do this, we're making sure that we split our points in half exactly every single time.
But won't some children like stop sooner than others, basically?
Yeah, but only by like one level. So it's like an even odd thing. So we're as close to splitting in half as possible at every single level. So there might be like an even odd thing at the last level, but otherwise it's like it will be as balanced as you could get. Yeah. Good.
So what's the pre-processing stuff then?
So this is what the sorting, or the almost sorting that we're doing here, we wouldn't do for a normal binary search tree. We rely on rotations, but we could do that for a normal BSD if we wanted. Right? We could sort our data, and then it would be really easy to construct because we only have to do that once, because we don't have to deal with these flipping dimensions. But yeah, we usually don't in practice. Other questions?
I was just gonna say that our algorithm, when we're splitting, we didn't deal with anything on that right side, but it would split all the way down on, so I have the left of our diagram there, and then it would come actually back and do the other side of the tree with our algorithm, right?
Yeah, the order that we do this, we would, it's kind of a, I guess it's kind of a reorder, a post-order traversal, and that we're going to go all the way down to a child. We're going to do the children and then kind of work our way up. Well, or maybe pre-order because we're doing the P first. Yeah, it's kind of a weird traversal. Cool. So the next thing we're going to talk about is the KNN. Doing the KNN query on here, where I want to know basically, for this point, give me the K closest neighbors. So we talked about a little bit of just kind of a sketch of how this would work with the quad tree yesterday, but we're going to go into pretty good detail about exactly how this works. And we're going to do this recursively, of course, because we have a nice tree structure. All right, so really our main function is going to be this KNN recurse. Starting at an N, at some node. And then we'll talk about kind of the rest of the information that we need to make this happen. Okay. So the tricky thing about this compared to the range query is that I kind of don't know ahead of time, just from looking at a point, whether or not I want to include it in my output. Okay? So for the range query, if I get to a point, how do I know if it should be in my output or not? I just look at the distance to my query point, and if the distance is less than my range, then I include it, otherwise I don't. Okay? For the KNN, I have no idea, right? If my distance could be 10 to the minus 10, and it might still be the K plus first point, farthest point away. Right? I don't know, it depends. It really depends on what other points are in my data set close to the query point. Okay? So the tricky thing here is I kind of can only, do like a best so far kind of thing. Say like, well, this is closer than anything else I've seen, so it might be in the output. So let me, it's kind of like a tentative output point. And then I'm going to kind of update that as I go along. Does that kind of make sense? So what I'm actually going to keep track of as I go through here is a priority queue. Of the best K points I've seen so far, and then I'm going to use this to kind of guide my search. Cool. Yeah.
What priority do you necessarily? Because as you traverse down, aren't you guaranteed to come to a
Not necessarily, right? So here, right? So maybe my point's over here. Maybe I look at this half first, and then I look at this half, right? So there's no obvious relationship between the traversal order and getting approaching the point P.
But are you doing some comparison?
Yeah. Yes, but there's still not really a guarantee that I'm going to see things in closeness order. So we'll see. We'll actually need kind of one more parameter here, but we'll fill that in as we go. Okay. So let's start here. So I want to do a KNN search at this node. All right. So I'm looking at this node. I have a point here. How do I know if I should add this this point to my data set or to my output? So as kind of an easy case, imagine I'm starting at the root. Okay? So when I start my query at the root, what's going to be in my priority queue? Nothing, right? So should I add the point at the root to my queue? Sure. Yeah, I've seen nothing better, right? There's no reason for me to suspect that the root is not in my output, right? So in general, right, if I haven't seen k points, then I definitely want to add this one to my output because I might not see more points. This might be the last one I'm looking at. Right? So if my neighbors size is less than k, right, then I want to add this point. So if I haven't found k neighbors, I definitely want to add this one because I need to get up to k. Cool. All right. What if I am full? So I've already seen at least k points. How do I know whether or not this point here should be added to my output? Check what?
The end? Well, I mean,
yes, I think you're on the right track. What do you mean by end specifically?
the one you would drop if it should fit in there.
The one that I would drop if I added this one, and which one would I drop? The furthest,
Farther.
right? So if P is closer, if NP is closer than neighbors, dot farthest, dot P, we'll add two more things. So if my node's point is closer to my query point than the farthest point in my neighbors, right, then I should kick that one out and insert this one, right? So I want to remove neighbors farthest and insert n. So I have just seen something that is better than at least one of the points that I've seen so far. All right, and so I'm going to kick that last one out and insert this one. This is why we want the priority queue, right? Is because we need to be able to know the farthest quickly, and we need to be able to insert quickly so that we can still find the farthest. So the binary heap data structure is pretty cool. Looking at the biggest element is constant time. This is basically stored at the front of an array, which is nice. And then removing it is like a log time, inserting it as a log time thing. So it's a nice data structure. Cool. Does this kind of make sense? Right, so if we have seen something, if we have found something that's better than what we've seen, then we'll add it to our output, right? And you can think of what's happening here as our range that we're searching for just shrunk a little bit, right? So we had our furthest point of our K. You can think of as like this is the range I'm searching in. I removed that. I got a little bit closer, right? So now maybe my range got a little bit smaller. Does that kind of make sense? So I'm improving. I'm like shrinking in my region where the K nearest neighbors could be. What is that like region size? What's my like radius here? So how far away am I searching? Like, so it's infinity, right? So before I have K neighbors, right? My range is infinity. Once I get to K, it's finite. And as I keep finding better and better points, my radius is going to shrink down until it's exactly the distance to the K farthest point. All right. So this is like this is kind of the simple part. All right. And now we get to the slightly trickier part. So if we didn't care about efficiency, right? What I would do next is just call KMN recurs on a left child and my right child. Okay. But I probably don't have to do this, or I might not have to do this. Okay. When can I skip doing that? Just because my K is full doesn't mean I can skip it, right? Because I might find closer points in my left child. So if I run out of points, so I guess in that case, how would I know I ran out of points? It'd be null, yeah. So if I get to null, I should also not do that.
Can we check those points? Well,
so this will
yeah,
check those
put in
points,
words.
but I'd really rather not. I'm lazy. I'd rather skip this work if I can.
And then,
So let's say that my right child corresponds, or my left child corresponds to this region. And this is like my current kind of radius. I don't need to look at this, right? Because none of the points here are in my region. Or sorry, none of the points in this region could like overlap with this range. None of these points could be closer than the Kth farthest I've seen so far. Right? There's no way that any point in this subtree is going to kick out one of the points that I've already seen. Right? And so I should skip it. Does that kind of make sense? Yeah.
So that makes sense intuitively to me. But how does that, I guess, where does that store?
yeah.
So this is the tricky part, right? So I'm going to write it out. So basically, if the distance from P to So if the distance from P to the closest point in my left child's region, right? So here, the left child's region here. So we'll talk about how to compute this in a second. But if the closest point in my left child's region to P is closer than the worst neighbor that I've seen so far is to P, then there could be a point in the left subtree that should be in my output, and so I have to recurse. So I just said what we talked about intuitively in a seemingly more confusing way, right? But this is going to make it easier to actually write up in code. Okay. So we're going to talk about the two parts of this. We're going to talk about how do I describe the region for my left child, right? And then we'll figure out how do I find the closest points to P in a region. Cool. Okay, so how would you describe the regions that each one of these nodes kind of represents? So I have my tree, right? So this is my root, and then I have a left child and a right child. Right, so this corresponds to this point. This one corresponds, say, at some point there. How would you describe the region of space that this kind of half of the tree represents? Does that make sense? Yeah, so in this case, it's anything that is to the left of this line. Okay. So this one's kind of weird because like 3 of the dimensions are infinite. Right? As I get further and further subdivided, I'm going to get to stuff here where actually the region associated with this point is actually this rectangle here. Right? So this point, this subtree only contains points that are inside of this rectangle. Okay. And actually, for any point in my tree, I can describe it with a rectangle. And the convenient thing about this rectangle is that it's axis aligned. So so it's not like rotated or anything. It's like it's a boring straight rectangle, okay. Which makes it really easy to describe with 4 numbers, which are the left and right extent and the top and bottom extent. That kind of makes sense. So the region associated with the point is actually just there's 4 numbers. We call that commonly called the AABB, or the axis line bounding box. Right, and this just has basically left, right, top, and bottom. And this is how I can describe a region of space that corresponds to a node of the tree. So my root node, what is its region? What area of space can be found either at the root or below it? Kind of a trick question. It's infinite, right? The left edge of that box is negative infinity. The right edge is positive infinity. The top edge is infinity. The bottom edge is negative infinity. So I start out with an infinite bounding box.
Will it be bounded by your minimum and maximum?
It could be if I know those in advance. Right. How about the left child? what region of space could be here and below? But the top and bottom, have they changed? They're still infinity, left, still negative infinity. The right is now whatever my splitting coordinate was. Right, so it's going to be basically the x coordinate of the point over here. Right? Every time I go down a level, my region, one coordinate of my region is going to change. Right? It's going to become the split value of its parent. Does that make sense? So, you know, when my root has children, the right edge of its left child and the left edge of its right child are going to be changed. Right? When they split, right, the top edge of one child and the bottom edge of the other are going to change, and so on. Most of the regions are going to be finite. Right? After I get down a couple levels, everything's kind of on the inside, and they're nice finite things. But I'll have a bunch of boxes around the edge that have infinite extents. So the boxes in the corners are going to have 2, and then all the boxes on the edge will have 1, like infinite, that goes out. That kind of makes sense. So we're going to add one more parameter here. Which is the AABB for the region that this node corresponds to. Okay. It's easy for the parent to compute as we go down, and so we're going to kind of pass it down as we go. Right. Okay. So that's one part of this. Is we're going to talk about the regions of space that these subtrees correspond to as we go along. And then the other thing we have to talk about is how do we get the closest point to P in a particular region? So let's say I'm talking about this region here, right? My AABB, this is going to be the left, this will be the bottom. What about the top and the right? So those will be infinite here, right? There's no boundary there. Okay. And if I want to know the closest point in this box, or in this region to here, what is that in this case? It's like a trick question. The point itself, the point is in the region I'm asking about, right? So the closest point in that region to that point is that point itself. What about this region here? So if I have this rectangle here, I want to know the closest point into this rectangle, or in this box, to this point here. Where is that on my picture? It's going to be right here. How about for this one here? It's going to be this corner right here. Does that kind of make sense? Right, so we're finding basically the closest point. So either the point is in the region, in which case it's just the point. Otherwise, it's going to be on the boundary of the region, kind of in the direction of that point. Does anybody know mathematics yet?
You're just looking for, it's not an actual, like, so the first one you drew, directly to the left, that's just like a possible point. Doesn't mean that that's an actual point.
Yes. So it's not necessarily an input point. Yeah, it is just like a geometrically in the region.
It's possible that
It's possible that there's a point here. Yeah. Okay. Does anybody know mathematically what we did to find those points?
or y coordinate is 0 and the other coordinate is the same to the left coordinate value of that point.
Yeah, so this is my box here, my region here. And this was the point I was looking at. The mathematical operation that I did here is actually, it's called clamp. You guys seen clamp before? So a clamp is basically, I just have a range of numbers. If I'm inside that range, I leave it alone. And otherwise, I just move it, I snap it to the edge of the range. Okay. So I took this point P, and I just clamped it to my box, right? So my y coordinate here was already in the range of allowed values, so it didn't change. My x coordinate was too far to the right, so I just snapped it to the right edge of my range. Right, and so I actually just did a clamp. Okay. So this closest point to is actually just clamp. And that works because we have these nice axis and line bounding boxes. We're just working with the x and y axes. And so this is all nice and easy to work with. Good. So now we have basically all that we need. Okay? So we kind of know we're going to talk about the regions that these subtrees refer to. And we're going to look at the closest point in those regions. And then we can tell whether or not we can skip out on recursing or not. So the region corresponding to my left child starts out as the same as my region, and then I make one update. All right, I have to change. So, here, so for my root, right, my region is all infinity. Which value do I change for my for my left child? So now I have just this half over here, right? 3 of my 4 fields are the same. Which one changed? So the right has now changed. I'm going to rewrite these. As the min and the max in each dimension. Okay, so my left is now min 0, my bottom is min 1, my right is max 0, my top is min 1, or max 1, sorry. Okay. So here, my left region is actually, I just have to change the max in this dimension to be what?
That section, I got lost when you said that it was the right region and then the min max.
Yeah, so instead of calling this bounding box, instead of naming these all these things, I'm going to rewrite them. So I'm going to have the min for each dimension. So that would be the left and the bottom, and then the max, which will be the right and the top. Does that part make sense?
I think so.
So if I have 3 dimensions, then I'll have 3. These will be length 3. These will be length 3. Okay. So my root. Right, my root node has all of its values all of its mins are negative infinity, all of its maxes are positive infinity, right? Because anything could be in my root. Its left child, the y dimension, the y min and y max are still plus and minus infinity, and the x min is still negative infinity, but my x max has changed. Because I know I have a hard limit here. My left child, none of this stuff could be part of it. I'm only on this side. So I've added I've cut off one, put one line in my box to cut off everything in one direction. And so so what is the actual value that I'm gonna like chop my box off at? Yeah. This is my point that I'm storing at the root. The x coordinate of this is where I'm chopping off and saying my left tree is all on the left side of it. That kind of makes sense. So, if my left child's region is farther away than the worst neighbor I've seen, right? If every point in that region is farther away than the worst point I've seen, I'm just going to skip it. I don't need to look there at all. Yep.
What if your priority queue is not full?
Then I wouldn't. I see. Good point. Yeah, what would change here?
You want to recurse?
Yep. So I would say if PQ, if neighbors size less than K, or all this stuff. Good catch.
So why don't we need to add that if we already have it, neighbor size is less than 3 neighbors and stuff?
So here we're looking at the point at this node, and now we have to decide whether we should look at our children. So if I added like point, if I'm in the root, I just added the first point, I definitely need to look at at least one of my children, right? And these are kind of independent decisions. It could be that this point at this node is farther away, so I shouldn't add this to my neighbors, but my children might have points that are closer, so I still want to recurse, so that could happen too. So this is a little bit more complicated than the range query, because this part is a little bit more complicated. This part is just slightly more complicated, but it's basically the same principle for the range query. This AABB region that we pass down, that's handy for the range queries for the quad trees and for this as well. Yeah. Any other questions about that?
Could you say again what that or statement is?
So this is saying if the neighbor size is less than K. So if I haven't seen K neighbors, I have to recurse no matter how far away my region is. Otherwise, if it's already full, then I can call leaves if they're far away, or I can call children if they're far away.
Thanks. I can really look at what is the line under the left region?
So this says if the neighbor's size is less than K.
The one upper.
Oh, here?
Yeah.
Oh, it says the left region dot max. So basically what I'm doing here is I'm shrinking one side of my box because my parent is splitting on that direction. So if we look at this point here, so this is my node. These are my left and right children. My left child, its box is the same as its parent's box, except its right edge got moved over. And for its right child, right, it's the same box as the parent, but its left edge got moved over. Does that make sense? So I'm saying I have the same box as my parent, except that one edge got moved in because that's like where I split. That's where my parents split, right? So I have to be on one side of that. Any other questions on this? So, compared to the quad tree, the really nice property of the KD tree is that it's not particularly sensitive to the dimension of the data. Because we're always, like, the number of levels only, and the number of children is fixed, right? It's only a binary tree. And the number of levels only depends on the number of points I have, not their dimension, okay? So in smaller dimensions, the little boxes that I construct as I like chop stuff up are going to be smaller. They're going to tend to be smaller. But even if I have a lower dimension, right? So if I have 2D points, I'm going to cut into little smaller boxes. Whereas I have the same number of points in 3D, my cubes are going to be a little bit bigger. But I'm going to have the same number of them regardless of the dimension, which is pretty nice. Cool. Other questions about the KD tree? We'll talk a little bit about one last data structure that's kind of like the KD tree, that I think is just a really fascinating data structure. And it is basically the same structure as my KD tree. I have nodes, and it's a binary tree, and I partition my data in half at each level. Right, I have left children all have some property, right children all have some other property. But this tree ignores the dimension altogether. Okay? It's kind of a weird idea, but it's very clever. This is called a VP tree, or a viewpoint tree. And it works like this. So at each node, I store 1 point, just like the KD tree. I select this point, I think, at random. So I just pick whatever point I want. Okay, so this is my root point. And so the way I partition the left and the right half is I sort the rest of the points by their distance to this point. The left half are all of the left subtree is all the points that are closer than the median distance to this point. And my right half is all the points that are farther than the median distance to this point. So what it kind of looks like is basically I'm finding a circle. So this is my left subtree, and on the outside is my right subtree. So I'm still splitting my points in half, but this time it's kind of like an inside-outside thing. Okay. So what I store at my node is P and R, right, where R is the median, is basically the radius of this cutoff circle. And then I do basically the same thing. I do my searches based on something like this. Question?
You just sorted all the data, wasn't this whole thing to avoid that?
Well, so we would do the same. We would do the same nth element thing.
Okay.
Yeah. So we do nth element, but this time instead of being keyed on the x coordinate or the y coordinate, it's keyed on distance to P.
But I guess it's based on distance to P. We just do an nth element for the number of points you want for the region. Like, does that make sense?
Yeah. So this is all pre-processing. So when I'm building my tree, I'm doing this. And so this is going to give me the same. It's going to be a binary tree that looks just the same as the KD tree, but the way I've chosen what goes where is different. And once I've constructed this, I can do fast queries. So the next thing I'll pick another random point. right here. And then I'll do the same thing again. So this time the region corresponding to this one is no longer really a circle because it's like the points that are outside of here aren't considered. But it's the inside here. So I've kind of split it into this region. So you have these really weird, like overlapping, intersecting circle divisions to cut your space up as you go further and further down this. Let me see if I can find a good picture. So the really neat thing about the VP tree is that it does not depend on the dimension of the data at all. As long as I can compute a distance between points, I can make this tree. I just have to compute distances. We'll see some other algorithms where that's pretty important, right? I don't actually have to be able to the points don't really even have to make sense to be in space. I just have to be able to find out how far apart they are, and then I can do stuff like this. So, yeah, here's a couple of VP tree pictures, which I think are pretty cool. So here's an example of a KD tree. Here's what it looks like. All right, so where's my root in here? How can I find my root?
There's the one that goes all the way across.
Yeah, the root is the one that's going to go all the way across, which would be this point here. It would be this point here, and then its children would be which ones? Two blue ones, right? And then the grandchildren would be these ones. So that's what the KD tree looks like. It's got these splits. All right, here is a VP tree, and it looks, I don't know, I think these look really cool, right? So I have my 16. And a visualize from there.
I think they're visualized based on their outline and color.
Yeah. So the first, I guess this is the root node, which is confusing to me because everything is inside of that circle, so I'm not really sure what's going on there. But then my next ones are split based on another distance, and then down here I have these splits inside of the gray circle. So yeah, this really weird decomposition of points. So I think these examples are a little bit better. So here's just what the construction looks like. So I pick a point, I find the median radius, and then I separate into inside outside. Okay, so this is my root circle. Okay. And then for its left child, I look at all the points inside of its circle, pick one at random, find this median split, and so this is my left, this is my left, right. These are going to be my right, left, and these will be my right, right. And so you keep constructing this, you get these really cool subdivisions. So this is totally irregular, right? With the KD tree and the quad tree, it's just these nice, axis aligned lines, nice perpendicular. Here you get these weirdly intersecting circles of different radiuses. Just really, really cool data structure. So for the searching, we do basically the same kind of thing we do with the KD tree or the quad tree, right? We try to partition our space, right? We look at basically for our query point, we find out if it's farther or closer to the point we're looking at compared to our radius at each node, and then we descend left or right based on whether we have to. So here's the case. So the query point is we're looking for points around this red point. The blue point is our node, and this is the circle for its node. Right. So here we know we have to traverse right because we're interested in the points that are outside of the blue circle. If they overlap, we only have to look inside. If they intersect, then we have to look inside and outside because we could have some points in here, or we could have some points out here. So that's kind of the idea. So these are KD tree and a VP tree of the same data. So another pretty cool data structure, I'd say. This is so here we're looking at how many nodes we can cull. So it looks like the KD tree is better at improves its search faster in general, but for dimension 15, we're trying to split in the KD tree. It takes us 15 levels before we go back to splitting on X again, right? And so the VP tree, I guess, allows us, because it's only based on distance, it allows us to cull our children faster. And so for really high dimensions, it looks like the VP tree could be better. So yeah, just a really interesting data structure that is similar to the KD tree, but that's kind of a different geometric way of splitting the data. All right. So this is been our KNN week. Right. So hopefully, so doing the KNN itself, the classification technique, pretty simple. The means to accelerate finding the neighbors can be pretty complicated, but hopefully everybody appreciates the cool geometry. We're going to be implementing the bins, the quad tree, and the KD tree for the next assignment. If you implement the KD tree, the VP tree should be pretty easy to code up. So if you find yourself a little bit extra time, I encourage you to give that a shot as well. And that assignment will be out next week. So be sure you take a look at the scraping and regression homework over the weekend, and otherwise I'll see you Tuesday.